Most astronomical observations depend directly on the exact position of the observer on Earth. The imaginary terrestrial equator and the prime meridian divide our giant planet into hemispheres. Any point on the Earth's surface is always absolutely precisely determined by latitude and longitude. However, the real Earth is a complex spheroid, so scientists distinguish three different types of latitude.
Welcome. Today we're going to conduct a really rigorous examination of the coordinate system we use to define any position on Earth. We'll start with a simplified, kind of ideal spherical model, and then move into the geometric complexities that are absolutely necessary for high-precision geodesy and positional astronomy. So, here's our roadmap. We're going to follow a pretty logical progression. First, we'll nail down the foundational concepts, the Earth's rotational axis and the equator. From there, we'll build up the coordinate grid of parallels and meridians. Then we'll define latitude and longitude on that ideal sphere before, and this is the interesting part, we confront the physical reality of the Earth as a spheroid, and you'll see that that reality requires three completely distinct definitions of latitude. All right, let's begin with the fundamentals. You know, to build any planetary coordinate system, you first have to establish a primary reference frame. For Earth, this frame comes directly from its most basic dynamic property, its rotation. I want you to visualize the Earth as a transparent body for a moment. The axis of rotation is a vector that passes right through its barycenter, or its center of mass. This line pops out of the surface at two exactly opposite points, the North Pole, which we'll call P sub n, and the South Pole, P sub s. Now, this definition sets up a really critical convention. Imagine you're an observer positioned out in space, looking down on the pole Pn. From that vantage point, you'd see the planet spinning in a counterclockwise direction. This simple convention actually defines the orientation of our entire coordinate system. Okay, so we have our axis. Now, picture a geometric plane that slices right through the Earth's center of mass, and it's oriented to be perfectly perpendicular to that axis of rotation. The line where this plane cuts through the surface defines a great circle. That's the terrestrial equator. And this circle, of course, cuts the globe neatly into the northern and southern hemispheres. So now that we've established our primary references, that rotational axis and the equatorial plane, we can go ahead and construct the spherical coordinate grid. This is the grid that's going to let us uniquely pinpoint any spot on the surface. This grid is made of two sets of lines. First, we have the parallels. Just visualize a whole series of planes, all parallel to the one we made for the equator. Where they slice through the Earth, they form circles that get smaller and smaller as they get closer to the poles. Second, we have meridians. These are great semicircles that are formed where any plane containing the axis of rotation intersects the surface. And just by convention, we've designated the meridian that passes through the Greenwich Observatory as the prime meridian, our 0 point, our starting line. We are now, finally, in a position to define the coordinates themselves. But for the sake of clarity, we're going to start with an idealized assumption. Let's pretend for now that the Earth is a perfect, homogeneous sphere. So in this perfect model, the Earth is a sphere of uniform density with a radius of about 6,370 kilometers. Now, a really critical physical consequence of this idealization is that the gravitational vector, basically the direction a plumb line points, is always the same as the radius vector. It points directly toward the geometric center of the sphere from any point on the surface. It's nice and simple. Okay, so for any point O on the surface of this perfect sphere, its latitude, which we denote with the Greek letter phi, is the angle formed at the sphere's center. It's the angle between the equatorial plane and the line going from the center to point O. Visually, it's just the angular distance of the arc along the meridian from the equator up to that point. We measure it from 0 degrees at the equator to plus 90 at the North Pole and negative 90 at the South Pole. Longitude, or lambda, is defined by what's called a dihedral angle. So let's construct two planes again, and both of them contain the Earth's axis of rotation. The first plane is our reference. It contains the prime meridian. The second plane contains the meridian of whatever point we're interested in. The angle between these two planes is the longitude, and by astronomical convention, it's measured eastward from 0 to 360 degrees. Now, while that spherical model is a pretty good approximation for a lot of things, high-precision work, like in geodesy, demands that we abandon that simplification. We have to account for the Earth's true physical form. So where does the problem come from? Well, it's all about physical reality. The centrifugal forces from the Earth's rotation cause a bulge at the equator and a flattening at the poles. The result is a shape that's much better modeled as an oblate spheroid. What's more, the mass inside the Earth isn't distributed evenly. This means the local gravity vector, that plumb line we talked about, doesn't necessarily point to the geometric center anymore. And it's not even necessarily perpendicular to the spheroid's surface. And this departure from a perfect sphere has a really profound consequence. It means that for any single point on the Earth's surface, our simple concept of latitude has to be broken down into three distinct, non-equivalent definitions. This divergence really poses a central question, doesn't it? If the vector to the geometric center, the vector of local gravity, and the vector that's perpendicular to the idealized surface are all pointing in slightly different directions, which one do we use to define our position? Well, each of these three vectors gives rise to its own unique definition of latitude. First up is astronomical latitude. This is the one you can physically measure. Visualize a plumb bob suspended at a point. The line it traces is the local vertical. It shows you the true direction of the gravitational field right where you are. So astronomical latitude is the angle between this physical plumb line and the equatorial plane. You determine it by actually looking at the stars. Second is geocentric latitude. Now, this is a purely geometric idea. I want you to imagine a perfectly straight line, a radius vector, drawn from a point on the surface directly to the geometric center of our reference ellipsoid. The angle this line makes with the equatorial plane, that's the geocentric latitude. And on a spheroid, this value is different from the astronomical latitude. And finally, we have geodetic latitude. This is the big one. It's the standard used in modern maps and for global positioning systems, for GPS. It's the angle between the equatorial plane and a line that is normal, meaning perfectly perpendicular, to the surface of the mathematical reference ellipsoid at that specific point. And importantly, this normal vector doesn't usually pass through the ellipsoid's center. So the angular difference between the true plumb line, which defines astronomical latitude, and the normal to the reference ellipsoid, which defines geodetic latitude, has a name. It's called the deflection of the vertical. And it's a direct measure of local gravitational anomalies. Its size is typically very, very small, usually less than 3 arcseconds. However, the difference between geocentric latitude and geodetic latitude is much more substantial and it's systematic. It comes purely from the geometry of the ellipsoid's flattened shape. This difference can get as large as nearly 12 arc-minutes at the mid-latitudes, so around 45 degrees north or south, and it disappears completely, goes to zero, at the poles and the equator. So let's just summarize here. The axis of rotation gives us our fundamental reference frame. From that, we derive latitude and longitude. But the crucial takeaway is that the transition from a simple spherical model to a more accurate spheroid model reveals that a single point on Earth can have multiple distinct latitudes, and this is an absolutely critical distinction for geodesy, navigation, and astronomy. We'll conclude with the practical implications of all this. Why does it matter? Well, an angular discrepancy of 12 arc-minutes might not sound like much, but on the surface of the Earth, that corresponds to a linear displacement of about 22 kilometers. 22 kilometers! If we failed to account for these different definitions of latitude, our high-precision global navigation systems would be completely useless, and it would introduce catastrophic pointing errors in astronomical observation. The distinction between an ideal sphere and physical reality is truly where precise science and engineering have to meet.
Thank you, friends. Strive for understanding and become wiser. See you soon.